Hey, good to see you back again to do some more revision. I hope you're feeling pretty good about catching up on some of these skills. And in this revision topic, part 3, we're looking at algebraic expressions. And we're using Pearson's textbook again and looking at what the IB consider to be prior knowledge for the new course starting in, our first examinations in 2014, being taught in Year 11 in 2013. So what's an algebraic expression? Well, you'd have some idea, and you would know that it consists of letters and numbers and terms added or subtracted. And here's Pearson's definition here. Algebraic expressions are formed by combining variables and constants. How do we represent a variable? Well, we represent a variable by using a pronumeral or letter to stand for the variable, So if there is something unknown, like I think of a number, double it, add 24 and the answer is 76, all that sort of stuff can be written in mathematical form or mathematical sentences or equations using pronumerals to represent the missing quantity. So here we have a mixture of those. There's a pronumeral, there's another one, and there's a number of lots of that expression out the front. So all of the letters here are standing for, or for numbers. So they can be any letter, and we create then what's called an algebraic expression. So that's great. Let's have a look at what we are expected to be able to do at this stage. So come down here. And the first thing we're going to do is have some names for some of the algebraic expressions that we're going to use. And one of those names is polynomials, where poly means many and nomials comes from number in Latin, many powers of the unknown or the variable. And the one which you've seen, of course, so far mostly is the quadratic, where you've got ax squared plus bx plus c. The highest power here is x. You could think of the linear function mx plus c as a degree 1 polynomial, where we call the degree the highest power of the highest exponent or power of the variable. Now, as you know, the IB like to use good mathematical notation. So here we have some here. We're talking about the numbers in front of the variable terms here must all be real numbers. And the powers, the n values, here it is here, must all be positive whole numbers, right down here x to the naught or just 1. So we're letting those A expressions stand for the coefficients or the number of each term that we've got. And then down the end here, because there's no variable x associated with this term, we're calling that the constant term. All right, so there's a little bit of new stuff here. In this course, we will mainly go up to cubics. Cubics are where you have the highest power being x cubed in the expression. All right, so let's have a look at what we can do with this now. The first thing is, when we create these expressions, is how do we work with them and simplify them? And we get the expression from junior algebra there of like terms. So what terms are like each other? Let's look at this first one. 2x squared y takes 7x squared y. Let's put those up front and have a look at them. So they are both terms in x squared y. You've got 2 of them, take 7 of them. So you've got -5 of them. And then the x squared term is separate because it is different. It's not like the others. Very similar to saying, what do you do with 10 cats and you sell 2 cats? You have 8 cats. So instead of cats, we've got like terms. Let's say something like 10x squared y take 2x squared y would be 8x squared y's. Okay, so it's collecting up the number of terms that are the same. You will have done a little bit of that earlier. So simplifying algebraic expressions there. Now, the other things that you have done is expanding and factorising polynomials. Let's look at expanding, because expanding means you take two factors and multiply it all out to see how many terms you've got. And this is often taught as a process called FOIL, where you multiply the firsts, the lasts, the inners, and the outers. That's a way of remembering how to get all the terms that are meant by the factored form. Let's have a look at this one up here. I think a good way of looking at it is what Pearsons have done here, is to say if we have 2x take 3 lots of x plus 5, then that's 2x lots of x plus 5 take 3 lots of x plus 5. And so it's 2x by x is 2x squared, 2x by 5 is 10x, check those off, neg 3 by x is neg 3x, neg 3 by 5 is neg 15. That's another way of ensuring that you multiply every term in the first bracket by every term in the second. In other words, you're doing the FOIL process. Then if we collect the terms up, there's only one x squared term, that's 2x squared, but there are two x terms, so 10x take 3x, 10 cats take 3 cats is 7 cats, and then 15 is the only numbered term. So it's our simplified. Now this is the expanding idea. Factorising is the opposite process, isn't it? Putting it back in the form of two factors. So when we look at this, 2 brackets times, each of these are called a factor. A factor is a term which, multiplied by another, gives the original number, or the original expression, or polynomial in this case. So here we also do factorising as well as often expanding. So let's have a look at x plus 3 squared, and that's x plus 3 by x plus 3, and you can do it again, doing it in full. And here x plus 3 is a linear term, a first degree binomial because it's got two terms in it, and we are going to expand those. So I don't know whether you remember, this is a certain pattern, isn't it, from junior maths. A plus b squared is a squared plus 2ab plus b squared. You might remember that's a special case because, of course, you always get over here a repeated middle term. So you get 2 lots of those, and we can summarise it with that formula. So I hope this is making a bit of sense. We'll practice in a minute. But coming down here, what would you do to cube a linear or first degree binomial? 2 terms in each bracket, highest power is 1, so it's linear. What do? Well, we do 2 at a time. So we do those, leave this one out the front, and then apply it, expand it, and do it in another stage. So it's x lots of x squared plus 2x plus 1 plus 1 lot x squared plus 2x plus 1. When we do all that, we can collect up the terms that are like each other. 2x squared and x squared makes 3x squared, x and 2x make 3x. So you're getting the idea of how to build these polynomial expressions from multiplying or expanding linear binomials here. All right, so let's come down and have a look. We're going to look at some special cases. We just looked at one a minute ago where the 2 factors were identical. A plus b all squared is a plus b by A take B, I want you to be able to remember this is, oops, no, A plus B by A take B is wrong. A plus B by A plus B. A squared plus 2AB plus B squared. This is called a perfect square form because there's two factors that are identical and you're therefore squaring it. But what about this where you have a difference in sign between the two terms? They're actually called conjugates. They're given a special name because when you multiply them out you might remember, and here we are, making sure we do all the FOIL multiplications. And look at this, wow, because it's x take 5 and then x plus 5, the middle terms cancel out. Neg 5x plus 5x gives no x term remaining. No x term remains. So that's another special case. You actually only get two terms at the end. You get the first one squared minus the second one squared, and that's called the difference of two squares in here, or DOTS if you like, difference of two squares. So what's the summary, the general rule for that? If you have A plus B by A take B, at this stage you're expected to recognise that form as A squared take B squared, or the difference of two squares. So please now try to go straight to the answers and not go through the whole FOIL process for this type, because that goes back to year 9 and 10 work. How are you going there? Remembering some of this? Well, we'll get a chance to practice in a minute. So here's a summary of some of the patterns and what we've just been doing there. When you expand brackets, we're going this way, as you can see. This is multiplying every term in the first bracket by every term in the second bracket. And so you end up adding up the middle terms, A plus BX. The term down the end is the product of the constants, if you remember. And so you can build there. So these are the special cases we want you to remember. These we'll talk about a bit later. They are forms we'd like you to remember, but at this stage you would have to do them by the long expansion method. Do these two, multiply the result by A plus B, like you saw earlier in the presentation there of x plus 1 all cubed. So we will be wanting to go backwards as well, from the expanded form back to the factorised form. Remembering the factorised form means getting a product of factors in brackets there, a product of factors. So that can be quite handy in solving equations using the null factor law, if you remember from your quadratic theory. Okay, so these are identities are always equal. No matter what A and B values you use, the expanded form will always be exactly equal to the factorised form. All right, so let's come down and keep going, and let's do some perhaps little problems here now. So here are some for you, a little set. You might like to pause the presentation now and have a go at these. We've got the answers right here, like in the textbook. Pearson's have put the answers underneath. I don't know whether it might be a good idea to just do this to you. Do you want to do that? And so I don't show you the answers, and pause the presentation there and see how many you can get right. Have a go. All right, well, I'm going to return it now so we can see the whole thing. So here we are. I think most of these are okay. I want to go to the number 6, or number C, sorry, let's have a look here. Where is number C? Here we are. 5x cubed plus 3y by 5x cubed take 3y. I think that's different from the C they've got there. the c they've got there is 6x plus y by 6x take y. That's interesting. Let's have a look at putting in a different answer here. 6x plus y by 6x take y will be the first one squared minus the second one squared, which is 36x squared take y squared. So Pearson's put in the wrong problem there. Let's have a look at part D, 4h take 5 squared, this one here. So that is following the pattern of a take b all squared is the first one squared and twice the product, but the product would be a by neg b, so it's neg 2ab plus b squared. So can you see, I'd like you to go straight from here to here. 4h squared is 16h squared. 2ab would be 2 by 4h by neg 5, which would be neg 40h, and neg 5 squared, any negative squared is a positive. So you might have a look. The cubic one is just following the pattern, or put all the brackets out together like x squared plus 2. You can do it this way, by x squared plus 2 by x squared plus 2. Do these two brackets, get an answer, and then multiply it by each of these. What about the last one? Here we've got square roots, but they come out nicely with the if they're conjugates. Here it is, 3 plus 2 root 5 and 3 take 2 root 5. So that's going to follow the pattern a squared take b squared, the first one squared minus the second one squared. And gee, isn't this nice? Because 2 root 5 all squared gets rid of the radical sign, and so this becomes 4 by 5, squaring both the 2 and the root 5. 2 squared is 4. Root 5 squared gives you 5 back again, so that comes to 20. So that's going to be interesting later on when we want to simplify some expressions. Right, so you might like to go back over that, check and maybe look at the earlier part of the presentation to make sure, and check your textbook perhaps. Right, let's keep going now. Oh, here we've got something here that I just mentioned. The result of multiplying two irrational conjugates, and there we are there. Two irrational, so here they've got root signs in that can't be worked out exactly, but at the end we've come up with a rational or exact answer there. So that's going to be useful, as I mentioned before. Let's go down to another example. This is going back the other way now, where we want to factorise the expressions. So remember, factorising means creating factors. Factors are two things multiplied together to give the original expression or number. So I want you to play with those, and we're going to look in a minute. This is Year 10 stuff. I think the solutions there are nicely put. So I'll just come down here and show all the solutions. Can I get them on the one page? Not quite. So we'll do that bunch. So when you want to mark your work, come down and pause it, and then the other bunch will go there. So when you've done those, you can go back and spin it back. So here we are. There are 6 problems here. And the idea, of course, with factorising is if there is a common factor like there is in this first one, you usually take that out the front of the bracket first. So you can check that down here. So pause the presentation, have a go, and check your factorisings there and see what you think of those. All right, we're going to move on now and have a look at the guidelines that generally you would use here. So guidelines for factoring polynomials. Take out the greatest common factor. So if I've got 3x squared plus 9x plus 6, first thing I'll try to do is put a 3, then x squared plus 3x plus 2. Then I'll try to create my brackets. There we have it. Plus 2 plus 1. knowing that these two must multiply to give the constant, and then these added up, x by 2 is 2x, 1 by x is 1x, gives 3x. Do you remember that from year 10? And here we go, that's what I've just done here. Try to find factors of the number down the end that multiply together to give 2. That's 2 and 1, and so on. They suggest, and I fully support this, they suggest you try a logical trial and error approach to see if it factorises. So if 2 and 1 didn't work here, well, you can't try anything else. But if this was a 4, a 5 or a 6, you might have to try different combos of factors here and here by trial and error. There's not much point in trying to learn a rule to do this. So we just try different factors in these spots here, and indeed in the x term as well. So we'll see a bit of that later on. All right, how are you going? A lot to remember. It's over 2 years' work that we have to remember here. And that's the idea of maths, of course. Maths is built up from learning stuff in sequences, in a sequence, one thing after the other. And then we put them all together and accumulate our knowledge into bigger problems. So it's important to try to remember what's going on. What's an algebraic fraction? Well, an algebraic fraction, of course, is one that's got algebraic terms in it. So in other words, pronumerals, standing for numbers, not just your ordinary old fractions where you've got numbers only. Algebraic fractions involve the use of pronumerals. You can call them also rational expressions because they are ratio now. Ratio of two expressions here. So algebraic expressions can be called rational expressions. They've got pronumerals in them and they are written as ratios or fractions. Alright, so in this course Pearson's make the interesting comment here. Most of the fractions that we will encounter will have numerators and denominators at top and bottom lines that are polynomials. That is, it will have x's and powers of x's or a's and b's in both top and bottom line. Right, so what are we going to do now? Let's have a look at trying to work with algebraic fractions. We know a little bit about what to do with ordinary fractions, 3/7 plus 5/8 and that sort of thing. What do we do here? Well, to simplify these algebraic fractions, what we're going to do is to try to take out a common factor out of the top and bottom line. So when we look at this term, 2a squared and 2ab, we see they both have a 2 and they both have at least one a. So the common factor is 2a. Then what do I multiply 2a by to get 2a squared? That's an a. Take, what do I multiply 2a by to get negative 2ab? It's a b. So by a combination of taking out the common factor, then checking with the expansion rules, I can give this top line a tick as being equal to 2a outside of a take b. Can we do it down here? There's 6 as a common factor, a is a common factor in both, and we've got the highest power of b that will go into both is just b. So we'll put b out the front, 6b out the front as common factor. Then we say, what do I multiply 6b by to get 6ab? I need that little a in there, so I'll put that in the bracket. Take, what do I need to multiply 6b by to get negative 6b squared? Just neg b. So now, if a take b is non-zero, remember, provided that a take b is not equal to 0, can't divide top and bottom by 0, so a and b can't be equal. If they're not equal, that's what they've done, they've cancelled them, divided the top and bottom by the same number. So we get left 2a and 6b, then doing it again in numberland, what goes into 2? What 2 is 2, it goes once. What goes into 6 is 2 again, goes 3 times. So there's our final answer, a over 3b. What about something a bit more challenging? Okay, so let's have a look at this one here, 2 quadratics divided. Oh, the top line, did you spot it? A take b by a plus b. And in the bottom line, we need an x and an x to give x squared. Then we need 2 numbers multiplied together to give neg 2. So here we've chosen neg 1 and positive 2. So the winning term is positive. So the bigger number here, the 2, had to be positive. So you've got positive 2x, take 1x, leaving a positive 1x, which checks back here. The winning term was positive x. Now, of course, we need to try to cancel terms, and Pearson's has done this rather long method here. I think I'd prefer you to simply realise that 1 take x divided by x take 1, how many times, what do you multiply x take 1 by to get 1 take x? It's neg 1. So actually, x take 1 cancel into 1 take x neg 1 times. That's what they're trying to show here. So the answer is neg x plus 1 over x plus 2. I'd like to see a bracket there. Or you can do it in full, neg x take 1. So this is getting a little bit heavier now. Let's have a look at the last one. This looks very much like what we'll see in calculus. This will be in the second year of the course generally. And we have x plus h squared, take x squared over h. So let's expand that first term. It's a perfect square. First term squared, twice the product, plus the second term squared, minus x squared. So what are we left with? 2hx plus h squared. So let's factorise the h out. There it is. What do you multiply h by to get 2hx? It's 2x. What do you multiply h by to get h squared? It's plus h. So we've got our factored form, and then we cancel this, and we should, whenever we do that, and I didn't do it up here, proviso x plus 1 is not equal to 0. And with the proviso here that h is not equal to 0, because you can't divide by 0. So what's the answer here? The final answer is 2x plus h. So these are taking a little bit of a step up from what we've done in Year 10. Same principle, but see, it looks a little bit different with the bigger expressions. Let's come down now. And we're doing everything in algebra land that we've done with fractions before, with numbers. You've just got to be a little bit tricky and about working with pronumerals and algebra terms compared with numbers. And if you go to Huddy Maths Middle School, on that website there is an introductory algebra course that takes you right through from the beginnings of algebra, somewhere in Year 7 and 8, right through to algebraic fractions. So if you wanted to spend some time, you could go back and revise that algebra on Huddy Maths Middle School.wikispaces.com. Okay, well, let's have a look at adding and subtracting fractions. What are we doing? What's the rule? Well, let's have a look. 3/4. Now, what do you remember about this? 3/4 plus 2/3. You've been told, well, you can't add up quarters, 3/4 and 2/3. You must have the denominators the same. Let's change both of them to the same denominator. So the way we usually do that is to multiply the two denominators together. So let's call this 12ths, and our aim is to make this 12ths. Because if we have a bundle of 12ths and another bundle of 12ths, we can add up the total 12ths without a problem. You can't add up 3/4 and 2/3. It has to have common things. 5 cats and 2 cats is 7 cats. So, making the 4 into a 12, what do? Well, we're going to multiply top and bottom by 3, so we get 12ths there. You must do the same to top and bottom line, so the meaning of the fraction the same, because effectively multiplying by 3 over 3 is just multiplying by 1. We actually haven't changed the meaning of the fraction. Why have we done it? Because we want to find an equivalent form by which to compare the two fractions or join the two fractions together. So here we want 12ths in the bottom line, so we multiply top and bottom by 4. So this becomes equivalent to 8 twelfths. So this is the idea of making equivalent fractions. Probably done back in year 6 or 7. And we need to revise this because now we want to do it in algebra land. So once we've got this, we can say we have 9 twelfths plus 8 twelfths is 17 twelfths. We can add up terms that are like each other or of the same type. So here it is up here. Pearson's actually put it over BD and shown you what's going on. I want you to try and recall how you did it originally with numbers so that you can more easily switch across to the algebraic fractions. Okay, let's come down a bit. I don't know whether you want to pause the presentation here. From the textbook I've actually cut out the work solutions here because I was going to do them with you. I thought you might enjoy that. So do you want to pause it and have a go, or do you want to watch me do it here now? So pause it if you want to. We're going to go on with it now. Let's have a look at x take 1 on x over here. This is really x on 1. Take 1 on x. We want the denominators to be the same, so let's multiply the denominators together, and the common denominator would be x. Now, x on 1. If I want to make this denominator an x, I have to multiply by x. I must do the same to the top line, so it's equivalent to not change it, so it becomes x squared on x. Minus, this is already over x, so we leave that the same. So here we are, x squared take 1 on x is our simplest form there. Let's have a look at the next one. We have a plus b and a take b. What will the common denominator be? Let's put it all over one line straight away. A plus b by a take b. Let's make the common denominator the simple product. This has been multiplied by a take b. To get the new bottom line, we must multiply the top line by a take b. Plus, now what happens to this one? Well, a take b, that's this term here. To get the new denominator, we've multiplied it by a plus b. So we must multiply the top line by a plus b. So those two would be equivalent. And now over our, what are we going to call it? Maybe a squared, do we want to make it a squared take b squared? Yeah, maybe we will. So here, making it a squared take b squared, we've got 2a take 2b, and then, oops, let's get rid of that, that was from the wrong spot there. So here we've got plus 3, okay, and this is 3a, and plus 3b. So what have we got? 2a plus 3a. Let's bring those together as like terms. That's a. Take 2b plus 3b is plus b. Oh, I don't think I should have expanded a plus b by a take b, because if I'd left it like this, I would have seen that as long as a doesn't equal neg b, this actually simplifies down to 1 over a take b. So I was a bit quick to actually expand this. I should have left it in this form, ready to see a common factor and to divide by it. All right, so let's do the last one, the big common denominator here, because it will be the product of these two, 2x squared plus x take 6. So here now, this denominator has been multiplied by all of this. So you must multiply the top line by all of that to keep the meaning or the balance of the fraction the same. Minus now, this denominator has been multiplied by x plus 2. So we must multiply its numerator by x plus 2. Okay, let's go on now. This is quite a big E. So this is 2 by 2x squared is 4x squared. 2 by x is plus 2x. 2 by neg 6 is neg 12. We've done all that one. Now we've got this one to do. Use a bracket, because we have to take away the whole result of these expanded, which will be x squared. And then plus 2x. Take 4x. And then take 8. Okay, so a lot of work there. Over x plus 2 by 2x plus x takes 6. Which is, what have we got here? Now we need to unpack this. 4x squared plus 2x, take 12. Look up here, neg x squared. Now we better join these together first, hadn't we? This is neg 2x. So with a neg out the front, that's plus 2x. Just let's check that here, because it's in here. See, when we've got this neg 2x there, and we multiply by the neg out the front, it's plus 2x, and then this neg by neg 8 is plus 8. Quite a big one, this one. And then we've still got our x plus 2 by 2x squared plus x takes 6. All right, now we can collect up like terms. 4x squared take x squared is 3x squared. 2x here plus 2x is 4x. And then neg 12, let's have a look in there, neg 12 plus 8 is neg 4. All over x plus 2 by 2x squared plus x takes 6. Now we can leave it in that form here, because we can't actually factorise the top line. Well, actually we can factorise the top line, but it doesn't come up with a common factor, I don't think. Oh, no, sorry, it does. So we've actually got to go on and do some more work on this. So let's have a look now. We can have a look at this one. So this is 3x by x, and see if we can factorise it. Okay, so here 3x by x gives 3x squared, that's okay. Two numbers multiplied together to give 4. Well, 2 and 2. Now we want the biggest term to be plus 4x, so we'll have plus 2 there and take 2 there. Can you see it? Neg 2 by 2 is neg 4, but I want the biggest term to be positive, the winning term. So the positive 2 has to be multiplied by the 3x to get plus 6x. Look at what's happened. We can cancel that, provided that x plus 2 is not equal to 0. And so we get a simplified form, 3x take 2 over 2x squared plus x takes 6. Very, very important if you're going on with further maths to be able to simplify complicated things that you might be working with and realise that they do come down to something much simpler. Okay, now sometimes this idea is taught slightly differently. Let's see what's happening. A over B plus C over D. We've been multiplying the two bottom lines together and then multiplying this one by D on D and this one by B on B. And we get AD plus BC. Now that's good maths. There is a quickie way of remembering that. Not good maths behind it, but if you want to do it quickly, watch this now. I don't really support the idea, but it is a quick method. It's called cross multiply. And when you're doing it, if you're a good mathematics student, you would know why you're doing it. But to get to this end point most quickly, you can say, I multiply these two together and cross multiply this. A by D plus C by B. Okay, so you can get there with this quickie method. We would always prefer you know why it worked though. That you are making another fraction equivalent to the first one by creating a common denominator. All right, let's keep going. I hope you're not getting tired. Of course, the glory of these presentations is if you are, you can just stop me. I'll be there tomorrow. Come back and see you again. Okay, let's have a look at some hints that Pearson's have included in the text, and they're very good ones here. Why is this okay? A plus B over C implies divide all of A plus B by C. So that equals A divided by C plus B divided by C. That's okay. And also, I suppose, therefore, if you want to look at this, AC over BC is A over B. Let's see about that one. Because if C is not equal to naught, you can cancel top and bottom. And they do that here. But the problem with it is, if you do this, you can't cross out the C's here, because this implies all of the top line is divided by all of the bottom line, B plus C. So if you just do that, no, because you're not doing the meaning of the fraction. And that is the whole top line, A plus B, must be divided by the whole of the bottom line, not just the C part. So when they are added, where you have addition of terms, addition implies you cannot separate and cancel. Cannot separate and cancel. Because this is the real meaning here. You can't split that term. Okay, let's move on a little bit, building up a few skills here. What about a compound fraction? You've learnt this way back in year 7. Let's have a look. A compound fraction is when you have a fraction divided by another fraction. Now what have you learned back in junior school with this? AB divided by C over D. Let's make this one a bit longer. The teacher said you invert and multiply. A good little rule. Very good algorithm. But why? Why when you have 3/4 divided by 2/3? Why does that work? Why is that equal to 3/4 multiplied by 3 over 2? Invert and multiply. Well, very nice little proof here from Pearson's, where it says, well, if you had two fractions, here's the first one, divided by the second one. If you multiply, remember that dot there can be used for multiplication. If you multiply top and bottom by D over C, now that's not changing the meaning of the fraction, is it? We're multiplying top and bottom by the same thing, same as multiplying by 1. Look at what happens to the bottom line. The bottom line becomes 1. So that's AD, in the top line, AD over BC, all over 1, or just AD over BC. And that's where teachers get the rule down here of invert and multiply, because it works. Okay, so that's a little rule or pattern because it works, but the real maths behind it is nothing to do with invert and multiply. It's actually multiplying top and bottom of a fraction by the reciprocal of that bottom, so you're making it 1. And that's how you can get to AD over BC. So, again, the quickie method is maybe you think invert the bottom fraction and multiply, but it would be nice in this course if you remembered why that works. All right, let's go on and practice some stuff. So here are some little questions down here. Can we get them all on? I think we can. I could earlier. Okay, simplify each compound fraction. So we'll put it here. So let's have a look at what they've done. Getting a bit small to see in this first one. 1 on x plus h, take 1 on x. So what do we want to do? Here it is. Here's the common denominator. Multiply the two denominators together. And therefore you have to multiply the top line by x, and in this one you have to multiply the top line by x plus h. And then getting them together over a common denominator. You've got that. And then here's your invert and multiply rule, if you like. And there we have the simplest form. And here, of course, provided that h is not equal to 0. So getting a little bit harder, particularly, I think, look at this trick here. B1 is being called B on B. So, and 1 is being called B on B there. So what do you notice? Every line has a denominator of B. Makes it simpler. And then here we have a compound fraction. Invert and multiply. So we've turned the bottom one upside down and multiplied by it. Can you see it? It's important to be able to do it in algebra land with pronumerals, just like you might feel comfortable, I hope you do, in number land with 3/4 and 2/3. So the secret here now is to make sure you can do it with ordinary real numbers and rational expressions, fractions, so that you can move across and do it more generally in algebra land. Okay, so in this last one now, we've got some factorisation occurring here. X by 1 take 2x, neg 3 over 2. Here we're saying that you could see that 1 take 2x is common. So if we put that out the front, what do you multiply it by to get the first term? It's that x there. What do you have to multiply 1 take 2x to the neg 3 over 2 by to get 1 take 2x to the neg a half? I don't know whether you could spot that, but it's the power of 1. Let's unpack that. 1 take 2x to the neg 3 over 2 times 1 take 2x to the 1. Addition of powers, remember that from last presentation. It comes to 1 take 2x. Add the powers, neg 3 over 2 plus 1 is neg a half. So it does work. A hard factorisation to spot there, because what we're trying to do then is to simplify in here, and then we see a common factor and we can cancel that provided that x is not equal to 1. We can do a few other things here with the denominator. But we won't do that for the minute. It doesn't lead anywhere, and we are going to do things with square roots in bottom lines with irrational denominators very shortly. Let's go on for the minute, and there it is. Rationalise the denominator. We're almost at the end, and there's lots of problems so that you can actually practice these skills. So do you remember that we simplified this by multiplying top and bottom by the square root? So we've got a whole number in the bottom line, an integer denominator, we're called rationalising the denominator. So if we have an algebraic expression, we might want to do the same thing. And you can do it by multiplying by the conjugate. Because if you have a plus b root c in the bottom line, you multiply by a take b root c, look at what happens. First one squared minus second one squared, and you get rid of the root c term. So let's have a look at what they've done here. Rationalise this denominator, 2 over 1 plus root 5. So what are we going to do? Try to get this as a whole number. If I multiply by the conjugate, look at what happens. First one squared minus second one squared. And the root's gone. So it just comes to neg 4. Well, we must do the same to the top line though. Multiply it by 1 take root 5. So then multiplying it out, 2 by 1 take root 5, and we see we won't multiply it out because we can cancel there. And then just go on with a little bit of a simplification with that negative being multiplied through the top line of the fraction. Or you can leave it like this, 1 take root 5 on neg 2. Could be done that way as well. What about this one? Well, we can get rid of that irrational expression in the bottom line. What do? We multiply by its conjugate, the opposite sign, because coming along here, that will give us a squared take b squared. Difference of two squares, and whizzo, there we get rid of the root sign. In the top line, we must also multiply by root x take 1, remembering to keep the balance or the meaning of the fraction the same. You must multiply top and bottom by the same thing. And so we can see how to do that. Okay, well, here are our examples, and there's a lot of them here. Exercise 1.5, let's have a look. I think it goes down, 50. Goes down to 50 problems. So I would suggest you pause the presentation now and have a go at these. I'll perhaps do that and then move it up. So later you can spin it back and get the other section of them. You can pause that. I'm going to go down here and display some of the answers in sections so that when you're finished, so let's do the first 5. There's the first 5. So this will give you an opportunity to spin back and pause it to check your work. And then if we do maybe the 6 now, just there, 6 through 12. Slowly you'll be able to come back and look at that. And then we'll do 13 through 20. It's got a fairly good explanation of stuff here, I think. See what you think. Some of them are quite hard problems. This is where your teacher will come in. You need to talk to the teacher about these as well. So that's 13 through 20. And let's then go maybe 21 then through to 26. And then we'll go 27. Let's just bring it up here. 27 through 32. And then we'll go 33 through to 40. Where are we? 40. And if we keep going, 41 through to 48. They get some pretty good explanations here. I think that's good. And then the last two, 49 and 50. So by going ahead like that, you can spin back and have a look. So I'm going to return you back to the first set of problems. Just here now. Exercise 1.5, so that you can have a go at those. All right. I think we've got a little bit of a gap in here. Some missing there for the moment. So you'll have to leave those half a dozen out. You might have to look at those in the textbook then. But what I'd like you to do now is to have a go at those problems, and you might need to get some help from a teacher for this one. This is taking algebra on a bit further than what we've done in Year 10. Right, well, look, keep at it. You're building up a lot of skills. And this will be very helpful for the remainder of, or in this new course that is coming up. Now, as I said to you before, I've split it, so there's one more revision topic, and that's on linear equations and simultaneous equations. So that's a fair bit of revision. I think that one's a bit friendlier. So I hope you'll join me for that. So work hard. It's cheers from me from now. Eh? What's that? It's cheers for now from me, and I'll catch you in the next presentation. See you then.